So in this example, we're going to find the exact value of cosine of a difference of two inverse trig functions. So cosine of sine inverse of 5/13 minus tangent inverse of 3/4. And the 5/13 and the 3/4 are chosen from Pythagorean triples to make the calculation a little bit easier. But this is going to be a multi-step problem, and probably it'll take more than one page in this note-taking software. So to get started, I'm just going to call this first angle, I'm going to call this alpha. Alpha is whatever sine inverse of 5/13 is. And then this angle, I'm going to call beta. Beta is whatever tangent inverse of 3/4 is. Now, you could just type the whole thing in the calculator, but as I said in the previous video, that's not always available to us. Sometimes it's not that we're calculating a numerical value, we are dealing with something symbolically. Maybe we have cosine of sine inverse of x minus tangent inverse of y. There's two input letters, and we have to come up with a formula as a result. Kind of like we did previously with like cosine of sine inverse of u. We had to do this symbolically. We didn't have numbers to work with. So we're going to go through the process of doing this symbolically to get the exact value. So once I work out what alpha and beta are, well, I'm going to use them symbolically again. I misspoke. I don't need to find them numerically, but I need to find out the sine and tangent values of alpha and beta respectively. So once I do that, this is just equal to, using the difference angle formula for cosine is alpha minus beta. Oops. This is going to be cosine alpha, cosine beta, plus sine alpha, sine beta. So I need to figure out what cosine alpha, cosine beta are, and then sine alpha, sine beta from the numbers given here. So I know that sine of alpha is equal to 5/13. Okay? And we'll deal with beta in a minute. Now, I know that sine inverse alpha equals sine inverse of 5/13. I know that the sine inverse function can only give you values in quadrants 1 and 4. Basically, we can only get values between, let's say, negative pi over 2 and positive pi over 2, right? Quadrant 1, quadrant 4, or in other words, negative pi over 2 to pi over 2, right? Now, here sine of alpha is positive, which that means that we have to be either quadrants 1 or 2. Quadrant 1 or quadrant 2, or in other words, we're in the interval 0 to pi, right? Now, if we consider those are the possibilities, the fact that we're dealing with sine inverse means we must be in quadrant 1 or 4, and the fact that the sine value is positive means we must be in quadrant 1 or 2, we conclude, well, we have to be in quadrant 1 as a result. We can't be in 2, we can't be in 4. So, change color here. Quadrant 1 is possible for both conditions, therefore quadrant 1 is where we are. So I know for alpha, cosine will be positive. Now, here I need sine alpha, but I already have sine alpha, so that part's done. But I do need cosine alpha. So I have to find cosine, and I can either use a reference triangle or I can use a trig identity. I'll go with the Pythagorean identity. We know that cosine squared alpha plus sine squared alpha equals 1, right? So that means that cosine squared alpha plus, well, 5/13 squared is 1. So cosine alpha, cosine squared alpha, that equals, plus 25 over 169 equals 1. But I'm going to rewrite this as 169 over 169 because I'm going to need to subtract 25 over 169 on both sides, so I might as well do this now. When I subtract, I'll find that cosine squared alpha equals 144 over 169. And again, remember, we're in quadrant 1, so I know cosine is positive. That means that cosine alpha must be 12 over 13. So I found the cosine alpha value. So back up here in this difference angle formula, I know sine of alpha because I was given that essentially. I know cosine of alpha. So half of it's done, basically, although it started out a quarter done because I already knew the sine value. So now I need to find cosine beta and sine beta, okay? And I'm going to use the information that beta is tangent inverse of 3/4. Okay, so let's get to that. Oops, I need to add another page here. Hopefully I don't put these out of order. Here we go, add a page. Okay, alright, sorry about that. Okay, so we know that beta, oops, wrong pen, so beta is defined to be tangent inverse of 3/4. Right? Now, tangent inverse has the same range as sine inverse, so we know that we have to be beta is in, well, I need to write that there. I'll just say beta is in quadrant 1 or 4, and that corresponds to I added another page, hold on. Okay, put it after. Okay. I think it's just a display error that's still showing it. Yeah. Okay, there we go. Sorry about that. Okay, so that means also that tangent beta is equal to 3/4. So when tangent's positive, that's quadrant 1 or 3. So that means we know that, oh, we must be in quadrant 1 again, because tangent inverse only produces angles in quadrants 1 or 4, and since tangent is positive, we know that we must be in quadrant 1 or 3, therefore quadrant 1 is a conclusion that we have. So everything's positive, which is convenient. So now I just need to know what sine and cosine are. Well, one way to deal with that, and there's I can think of at least 2 ways. We'll do the one I think is going to be easier. Tangent beta being 3/4, well, that means since tangent is defined to be y over x, right? Y over x is 3/4. Now, if we can find what r is, then we'll be able to find sine and cosine. Now, x squared plus y squared equals r squared. So 4 squared plus 3 squared equals, you might see where this is going. Again, these numbers were chosen to be Pythagorean triples, so you can probably look at it and tell what it is, most likely. 16 plus 9 equals r squared, so 25 equals r squared, so the radius must be 5. Right? The radius value is never going to be negative. That's a possibility we'll deal with later, but here, how do you have a radius, a circle of radius -5? How would that be possible, right? There's actually something you can do with that in polar coordinates, but we'll deal with that in a later video, a significantly later video. So that means now that I know what r is, I can say that sine beta, well, this is y over r, right? And y was 3, so this is 3/5. And then cosine beta, this is x over r, so this is 4/5. So now I know sine alpha, sine beta, cosine beta. So when I go to find cosine of alpha plus beta, as I said before, this is cosine. It was cosine, wasn't it? It was, okay. And it was minus, actually, my mistake. Cosine alpha minus beta is cosine alpha, cosine beta, plus sine alpha, sine beta. Okay. Oops. This iPad doesn't like it when you write quickly. Maybe I should just, it's trying to tell me to slow down a little bit, perhaps. So cosine alpha, what was that? 12 over 13, okay. And then cosine beta was 4/5 plus sine alpha. Was that 12 over 13? 5 over 13. 5 over 13. Times 3/5. Sine beta is 3/5. Yep. Okay, so this is a little bit easier than other examples where we have lots of roots and messy numbers. These were chosen to be relatively easy numbers. So I get 48 over 65 plus 15 over 65, and we can combine those and get 63 over 65. So that is cosine of sine inverse of, what was it? Cosine of sine inverse of 5/13 minus tangent inverse of 3/4. So this kind of problem is really lengthy. There's a lot of things to consider because you are using a difference angle formula. You are doing composites. You have to use either a reference triangle or identities, or use the Pythagorean theorem to work out what these values are. So it's fairly involved. It's not a simple problem, but this is a relatively straightforward example because the numbers worked out nicely.